Alright, so let's take a look at 2.6 number 22. 2.6 number 22 says, determine intervals on which the following functions are continuous. So in this case, let's see, s of x equals x squared minus 4x plus 3 over x squared minus 1. So, anytime I see a quadratic in the top and a quadratic in the bottom, I always think, can I factor? Is there something that I can eliminate? If there is, it's very possible that this function might get a bit easier. So I'm going to start by seeing if there's any factors here, if there's any common factors between the numerator and the denominator. So up top, let's see if we can factor this. X squared minus 4x plus 3. So maybe x minus 4, x plus 1 maybe, or x minus 3, x plus 1, that's x minus 3, x minus 1. Let's just try this real quick. X minus 3 and x minus 1. That looks like it might be our guys, because we get x squared minus 1x minus 3x gives me my minus 4x, but then minus 3 times minus 1 gives me plus 3. So that works out good. And you might recognize the denominator here as the difference of squares. Difference of squares means when I've got something that's squared here and something that's squared here, because I can write 1 as 1 squared and it gives me the same result, then it's the difference of squares when there's a negative sign in the middle. Anytime that's true, it just becomes x plus 1, x minus 1 in this particular case. If it was x squared minus 9, it would be x plus 3, x minus 3. You get the idea on that there. All right, so interesting to note here, though, take a look at what's going on here, is that we end up canceling out an x minus 1 there. So s of x actually is equal to x minus 3 over x plus 1. And now you got to ask yourself, what is continuity again? Well, continuity really means it's the places where I can draw the function continuously. You can imagine keeping your pencil on the paper the entire time without having to pick your pencil up. There is a spot here where I can see that x cannot equal negative 1. That means it is not continuous at that point. So in this case, I would say, a number of ways you maybe could write this. S of x is continuous for all real numbers except at x equals negative 1. Or you might write, that's one way of writing it, or you might write s of x is continuous on the interval, and you could say negative infinity to negative 1, but not including it, so no square bracket, in union with negative 1 to positive infinity. And this is again a case where I might like to just graph this thing and see what I'm talking about here. See if this thing graphs out the way I think it's graphing out. So I'll go up to the top here, and I'm going to type in the original function. So that was my analytical approach to that, where I thought x equals negative 1 is a bad spot. I'm going to do a graphical approach now and just see what happens. X squared minus 4x. This was my original function. Oops, went the wrong way there. Plus 3. And then in the denominator, we need to put some numbers down here too, which was x squared minus 1. And so our original thought was that the only place we were going to run into trouble, if I look back at my slide, was at negative 1. All real numbers except at x equals negative 1. So what you're going to see is that's the point of discontinuity. So as I approach negative 1, guess what this thing does? It shoots off to positive infinity in this direction. As I approach negative 1, coming from the positive side towards negative 1, from the right, it shoots off in this direction. But the discontinuity is actually at negative 1. It's not allowed to equal negative 1, either heading this way, and it's also not allowed to equal negative 1 heading this way. So that's kind of interesting. Again, negative 1 in this case would be right in the middle here. So that just goes on to prove what we showed analytically. So.